Okay, so here we go. Happy Friday. We had a pretty in of all the things we teach you in a class like this, Calculus 2. What we're going to do now, and what we started, I should say, yesterday, is really, in my opinion, some of the most useful and important, the kind of stuff that will carry with you for many of you. You know, what we did a lot of so far, a lot of the integration stuff, as you guys know, this is, machines can do that for you, technology, but now we're trying to get you to think in a little different way about how to analyze and solve problems, not just compute and do procedures. So with that said, I posted a homework yesterday. I hope that you guys will look at it. I don't know how many of you got a chance to really look at it yet. But what I'd like to do is I'd like to talk about some of these problems and do some similar ones to give you a chance to work this stuff out. So before I do that, excuse me, does anybody have a question they'd like to ask about homework 10 at all? Specific one? Or should I just say what I want to say? I'll let you think about that as I sip my water. Water. Okay. So I don't see any questions. So here's what I want to say about this stuff. So our current topic is what we call Taylor polynomials. So let's just remind ourselves of what we showed yesterday. We defined them and discussed how they quote unquote approximate. So the obvious question would be, what do we mean by approximate? And that's actually a very difficult question, and it's not truly studied in a Calculus 2 course. In fact, it can deserve its own course, really, what we mean by approximating. And we try to illustrate these ideas on homework, and so we're going to do some examples to help illustrate that. So we did two important examples. So we showed that like e to the x can be approximated by a polynomial that looks like this. If I can only write it down correctly. So it's 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 5th. And of course, this pattern can go out to any place your little heart wants to stop. Or maybe you have a big heart, I don't know. So we gave this thing a name. Remember, we called this P sub n, the nth order.
For the term with 1 over 4 factorial, isn't it supposed to be x to the 4th?
It is. Thank you for paying attention. See, I knew you guys weren't sleeping. Very good. So you should notice a very clear pattern here. The exponent matches the factorial. Now, of course, someone is going to say, well, why don't you write 2 factorial? Well, I could have written 2 factorial. That's fine. And I could have written 1 over 1 factorial and then 1 over 0 factorial if I wanted, but that just seems redundant. I see a typo in homework 10 I already posted. I have problem 1A. There's a slight typo. Which I'll fix for you. Okay, so one of the things we want to notice is what happens if we graph a function with one of its Taylor polynomials. So let's go to Desmos, for example, and graph. We did this yesterday. We're going to do it again. So let me share this web page with you. Oh, you guys see Desmos? No, what do you see?
That's Desmos.
Yeah, you see, but I don't want the screen. I want just Desmos itself. Now you should see it better. Okay, so what I'm going to graph is I'm going to graph e to the x. And it looks like this. And next to it, I'm going to graph, let's say it's fourth or fifth. Let's do fifth, because I asked you to do fourth for homework. So hopefully you see me painstakingly type this in. So what I want you to pay attention to is where the graphs sort of, you know, quote unquote approximate. So what I'm asking you to put your eyes on is notice from about -2, right around -2 to the right, the blue is right on top of the red. And now if I zoom out, I realize that they start to separate. You know, what are the x values here? Well, you know, when is my approximation no longer that great? You know, maybe they start to separate right around 2.5. But you might say, looking at the graph, the following. But let me go back to my whiteboard. So if we graph e to the x and then p sub 5 of x, which is 1 plus x. Lydia, I'm busy, honey. What do you need?
Excuse me. Well, I'm trying to.
Lydia, what do you need?
I'm trying to get to the science kid on. The easier way is like to go like to find Netflix.
Yeah.
Not to say it, but I found like, and when you go to the bottom, like when
Lydia, I can't help you right
now.
Right now,
I
upstairs.
saw it.
Daddy's teaching right now.
Okay. Maybe was the one who went.
Lydia, you know how to get it, honey.
Hold on, Ricky. Daddy's teaching.
No.
Ricky, go upstairs, please. Ricky, hi, Ricky. Good morning. Okay, mommy can get to. Can you please? I mean, Ricky, good morning.
Later.
I'm getting you.
Ricky, go up with mommy.
Okay. So anyway.
Chaos, chaos, chaos.
So remember how he
Okay, so if we graph, sorry about that. Like I said, this ain't easy. Okay, so if we go all the way out to 1/5 factorial x to the 5th, and we graph these on the same axes, we note they look the same. Now, this is what I mean by that. I guess I'm just saying, intuitively speaking, on say -2, comma 2. So I hope this makes sense to you. You know, they look like the same curve. If I restricted my domain to, if I said, okay, -2 less than x less than 2, and I did that for the other guy, -2 less than x less than 2. If I did that and just looked at the graphs, I could even go change my, I can go and change how I'm looking at this thing on my, if I just go graphing and change my scale, you would say, okay, those look to be pretty similar. They're not exact, but they look pretty similar. So one way we could sort of quantify that, let's change color. What are you guys seeing right now? Are you seeing Desmos or the whiteboard?
Whiteboard.
Oh, well then how the hell am I supposed to make my point to you? So what I did is, if I just look at the graph, but I restrict my inputs, my domain from -2 to 2, now these two things are very much indistinguishable. Now, if you really zoom in on the endpoints, you'll say, okay, I see that they're not perfect. But if you look at these graphs, you would say, oh, okay, I get it. And what's even more interesting is if I switch this view from 0 and I did this, what you might even say is you would say, oh, I've got a way of quantifying. Because look, here's the issue. How do we quantify how close they are, or how approximate they are? Well, one way would be to say, what kind of region do they make when we bound their graph with the x-axis? So to put into more specific words, what I'm saying is, note that we expect the integral from, say, 0 to 1 of e to the x to be very close to the integral from 0 to 1 of, say, p sub 5. So what I'm saying is if I instead switch this back to what we had before, if I now just looked at two areas, if I said 0 less than y less than e to the x, and I restricted myself between 0 and 1, I expect that green region to be, and I'm going to show you this back up, I expect this green region that I've shaded in here, which is the area under e to the x, I expect it to be almost the same, if, you know, approximately the same as if I integrated under the polynomial. So for fun, let's verify this like I asked you to do on the homework. If you look at the homework, I asked you to do this. Only with p sub 4, and I'm doing with p sub 5. So if I go back to my whiteboard, we can verify this. So what is the integral from 0 to 1 of p sub 5? Well, this is 1 plus x plus, I'm going to write it like this, x over 2, or x squared over 2 plus x cubed over 3 factorial. 3 factorial is 6. X to the 4th over 4 factorial. What's 4 factorial? 4 factorial is 24. And then this is x to the 5th over 5 factorial, which is 120. So what is this integral? Well, it's not going to take you too much time to know what this is. This is x, and then this is plus x squared over 2 plus x to the 3 over 6 plus x to the 4th over 24 plus x to the 5 over 120 plus x to the 6th. Okay, so what's 6 times 120? Maybe you don't know that. You go to a calculator and you get 720. And we are evaluating this from 0 to 1. So when we plug in 1, we get 1 plus a half plus a 6th plus a 24th plus a 20th plus 1 720. And then when you plug in 0, you get this. So I can now add this up. This is 1 plus a half plus 1/6 plus 1 divided by 24 plus 1 divided by 120 plus 1 divided by 720. So as long as I didn't make any errors. So what I end up getting is I get 1237 over 720, provided I didn't make an error, which is approximately 1.71806. Does anybody have a question with that? Any questions about this calculation? Okay, so you notice once again in typical O'Grady fashion, I did it exactly because I like fractions. I know some of you would go right to a computer. That's up to you, or a calculator. Okay, so that's the integral of the polynomial. Now what we want to do is integrate the actual function. So now I'm going to integrate e to the x from 0 to 1, which is e to the x. And when you plug this in, you get e to the 1 minus e to the 0, which is e minus 1. And so using a calculator, we can tell you what e minus 1 is. If we take e minus 1, we get the following. We get, we get 1.71828. So if you flip back a page, you'll see that we got the same number at least 2-3 decimal places. So here's what we got. And this gives us another way of calculating E. So we can rewrite as 0 to 1 e to the x dx minus the integral 0 to 1. I'm not going to write it out. P sub 5x dx. We can rewrite this as this, which is e minus 1. And then what is this? Well, if we go to the previous page, it was 1237 over 720. And now if you take these numbers and subtract, compute this value, we get approximately 0.000267 or 2622, excuse me. Mama, 2262. So what that tells us is that this polynomial is, as we suggested yesterday, has lots of uses, and one of which is it can help us compute values of E rather accurately. Because rephrased differently, you can now get a rational approximation of E. So let's write that down, because this is something that is of use. So if I take that minus 1 and I put it over 720, so if I take 720 plus 1237, so if I rewrite that, what this tells me is we have the following rational approximation. E is approximately 1957 over 720. And you can go to a calculator and verify that for yourself. And you're accurate to do 3 decimal points. Does anybody have a question about this? Going once. Going twice. So what I've just done is I've done problem 1 for you, only I did it for p sub 5. I'm asking you to do it for p sub 4. So I did the one that requires a little more work. Does anybody have a question or a comment? And then you're going to do the same thing for number 2.
So regarding the accuracy of this, is there a typical standard of how far you should go out?
Absolutely. Yeah. So again, we don't do that in this class, but I could say to you, Jeff, I could say, okay, dude, I want you to be accurate to 10 decimal places. then there's a way you can do it. And the theorem that provides that is what's called Taylor's theorem. We will talk about it briefly, but we will not do the analysis of error. That's just for, you know, the analysis of error is really a branch of mathematics called numerical analysis. I've hinted to this before, but you can absolutely analyze the error if you want, and we'll mention something about it, but we're not too concerned in this course with it. What we really want you to do is be able to work with it, and then we're giving you these examples that you can easily graph, so that you are, you know, you could even say, okay, yeah, it's clear these things are approximately the same. But if you really want to analyze error, that, like I said, there's courses, there's whole courses on that, and there's a whole branch of math that analyzes error and algorithms. And by the way, this is not how a calculator is going to compute E. I'm not saying that this is even a remotely efficient way of computing E. I'm saying it's a way. Does that make sense?
Yeah, definitely. Thanks.
Yeah. Perhaps years ago, when people were, you know, don't forget, I've said this to you guys before as well. You know, if you were a engineering student 100 years ago, you know, there was obviously no calculators, at least not one that you can put in your pocket or had in your house. So how did you compute values of like logarithms and sines and cosines? Well, you know, I mentioned this to you before. You used to buy books. And in these books, all it was tables of values. You know, much like some of you did in a probability and statistics, where you like went in the back of the book and looked on these tables. And those tables may at one point have been derived using polynomials, Taylor polynomials, to approximate, you know, E and pi and all that crap. But that's not how they do it anymore. They have very sophisticated algorithms for this. But nonetheless, what we're doing, we're not teaching you stuff right now. That's not to suggest that this stuff is redundant or not used. Taylor polynomials are used all the time. It's funny, you know, I hear like physicists and engineers always joke all the time about how that's all they do is use a Taylor polynomial, use a Taylor polynomial. And the reason for that is it's nice to replace ugly things with easy things, like polynomials. Does anybody have a question? Okay, so let's do something similar to problem 3. Does anybody have a question? Hopefully that answered your question, Jeff.
Yeah, it did.
Yeah. So your book, if you have the book, actually talks a little in depth about error. And we will briefly, but again, it's a little too, analyzing error is a very complicated thing because it requires, and then this is not a knock on students in Calc 2, it just requires a higher level of what we call mathematical maturity. It's just, I've tried to do it in the past, and it seems like it's more painful and more, it doesn't help as much as it hurts. So, you know, we got enough hard stuff to learn. Okay, so let's look at another thing we can do, and this is useful for problem 3. So we can often use Taylor polynomials to approximate difficult and/or impossible integrals. So we've talked about a few of these. Let's do an example of what I mean by this. So if you look at problem 3, I suggested this integral we did, and we did this a few months ago. And I'm encouraging you to do it again, and then I'm also encouraging you to approximate it. I guess another typo. I gotta fix this homework. There are typos everywhere. What the hell's I gotta. Right when I'm done with this, I'm fixing your homework. I apologize. I must have been sleepwalking when I uploaded this yesterday. Terrible, terrible, terrible. I'm gonna fix these typo over because when I'm, you know, this thing. Anyhow, whatever. I'm getting off topic. So here's some examples. So let's look at compare with on the homework, okay? So suppose I want to integrate e to the negative x squared from, say, 0 to, I don't know, 0 to 10. Now, we know that we can't do this exactly because we don't know an antiderivative of e to the negative x squared. We've talked about this before. So we can't use
We have a chance.
the FTC because we don't have an antiderivative.
Can you go back to the slide?
Oh, yeah, I'm sorry. I didn't know you were talking to me before. I apologize. Let me know when you're ready. See, I keep going too fast. I feel like a jerk.
Okay, I'm fine.
You good? All right, so remember, if we wanted to just integrate this like we learned in Calculus 1, it's a no-go because we don't have an antiderivative for e to the negative x squared. So one option was to use numerical stuff. We did that before. So one option is to approximate with Riemann sums, with, Simpson or something. We did that already. So another is to use Taylor polynomials. So here's what I mean by that. So let's pick, I don't know. Let's go to Desmos and let's see about what well, actually, before we go to Desmos, let's say something. So we know that e to the x is approximately 1 plus x. Let's use the second one. So let's say x over 2, or x squared over 2 plus x cubed over 6. So we'll use the third order Taylor for this one. So if we know this, then we expect, now again, this goes back to Jeff's question, how accurate are these things? But we expect then if I replaced x with something, then I should expect that e to the x squared should be something like 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 2. Does that make sense? So if e is equal to something, then if I plug something into e, it should be equal to what happens, or at least approximately, what happens when I plug that into the other something. So notice that on the very bottom line, the power is increased because I was replacing x with x squared. And so if you go to a graph and check this out, and I'll show you that in a second. Let's go to our Desmos.
Can the denominator for x to the 6 still be 6?
It should be, yes. Thank you for paying attention today, guys. Should I be fired? I don't know. Maybe some of you do want O'Grady fired. That would be sad.
On what planet?
On what planet?
Yeah.
Well, this is true, Daryl. This is true. All right. Although I could never do this online forever. I would have to go get a different job. I hate sitting in a chair. You know, I need to be screaming and railing around and calling you guys numbskulls and stuff. All right, does that look better? I hope so. Again, notice the exponents on the first line are all the ones from the Taylor polynomial, but downstairs they all increase by a power of 2. X squared squared is the 4th, x squared cubed is the 6th. So if we go and graph these guys, if I go and graph e to the x, and I'm going to share this, you guys, let's go look at this. So I'm going to graph e to the x. And now I'm going to also graph, and I'm only really interested between 0 and 1. And now I'm going to graph that new Taylor polynomial. I had 1 plus x plus, excuse me, this would be x squared now. And then this would be plus x to the 4th over 2. And then it was plus x to the 6th over 6. Is that correct? No, that's not correct. What am I? So it's 1 plus x, that's good, and then x squared over 2x to the 4th, and then what happened? Why did we lose it? Did I write down wrong? Okay, so hold on. Okay, yeah, that's fine. Perfect. So I don't want y to the x, I want x squared. So if I graph e to the x squared and then this Taylor polynomial, you guys will see that between 0 and 1, is everybody seeing Desmos, hopefully?
Yep.
Yep. Yeah, you'll see that that red and purple are right on top of each other. Now, they're not perfect when we move away from the origin, but when we are between 0 and 1, they look really good. Okay, now, you might be saying, well, that isn't the function we started with. I agree, but we got to take baby steps. What we really wanted to deal with was minus x squared, right? So if we go back to our whiteboard, what we expect then is we actually expect the following. Similarly, we expect e to the negative x squared to be 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6. Now, you're going to say, why are there those minuses? Well, remember, we are plugging minus x squared in, and when you square it or raise it to any even power, it's positive, but when you raise it to a negative power, it's minus. So that's why I have this alternating thing happening. So let that sink in for a second. And now let's go back to Desmos and let's convince you that I'm not lying. So if I make the proper adjustments on the sign of these things, you will be in agreement with O'Grady that, okay, yeah, I get it. They are. Between 0 and 1, that's pretty good. So what does this mean in terms of what we're blabbing about? Well, it means the following. So what do we expect then? We expect that this integral, which we cannot compute exactly, should be approximately the same as this integral, which we clearly can compute exactly because it's a polynomial. So let's just do this. This is not a difficult integral to compute. This is x minus a third x. Well, I wrote this. This should be a plus sign. Excuse me. Then this is plus.
Are we going 0 to 10?
Yeah, well, that's fine. Yeah, we can do 10. My apologies. But actually, no, I don't want 10. I'm sorry. So let me fix this. That's a good point. So bear with me for a second. Thank you for pointing that out. If you go back to the original problem, I wrote 10, right? So I forgot to tell you that. Why would that be a bad thing? Well, look what happens if you go back to the graph. Look what happens. Our approximation dies pretty much after 1. It's no longer good. If you look over here, the red and purple are separating, correct?
Yeah.
Right? So we don't want to go to 10. So if I go back to the original problem, thank you for pointing that out because I forgot that I had a method to my madness. So that was the original problem. So let's be very, very clear what I mean. So we expect, and let me put this here, looking at the graph, that this is the same. So, however, and the main point, which I'll write down on the next page, if we wanted to go out to 10, we would need more terms in our Taylor polynomial. 4 terms is not enough. Does that make sense?
Yeah, I see where you're going now.
Yeah, so that was kind of the point of this. So let me finish this real quick and we'll make that comment on the next page. So this becomes x minus a third x cubed plus, and then when I raise to the power 5, I get a 10th x to the 5th. And then when I raise to the power 7th, I get 1/42 x to the 7th. And this is from 0 to 1. So I don't want to spend too much time on the arithmetic. So I'll just, you can verify this for yourself at a later date. This is 1 minus a third plus a 10th minus 1 divided by 42. And so when you compute this, you get 26/35, which is approximately 0.7428. So what I'm computing here is just the integral from 0 to 1. I'm approximating it. And now we're going to make the point that was sort of like the foreshadowing to come. So note, the integral 0 to 10 of e to the negative x squared would require many more terms than just the first 4. So this actually goes back to your question, Jeff. The question would be, how many terms, what order polynomial would I need for a good approximation? So what P sub n would we need? You know, n equals 50, 100. Do you get what I'm getting at here? So when we go back and if you look at the graph, you'll see they started to separate around 1. And that means if we tried to approximate it, we would get nonsense. So I don't know if that makes sense. I hope it's something. The point of this kind of problems are to help you learn this, but also stir your imagination so that you ask good questions like you just asked. I mean, that's a great question. How do we know how good it is? And how do we know how many terms we need? I mean, and as I said, those are the kinds of things that you answer in other classes. Now, you could experiment for yourself. You know, you could, what you could do, Jeff, is you could, or if anybody was interested, you could go to Desmos, and you could just continue this pattern. So say you went and changed your scale out to, say, I don't know, let's say I want to go out to 10. Well, you'll notice that I need to go a few more terms to make it match. So what's the next term in the pattern? Well, this would be plus x to the 8th. And then what am I dividing by? Well, you'd be dividing by the next guy. This would be 4 factorial, which is 24. That's not very good. And then the next guy is x to the 10th. And then you'd be dividing by the next guy, which would be 5 factorial. So let's just do 5 factorial. Now you see that's getting a little better. So you might sit here and investigate for a while. How far out do you have to go to do this? Now it is a question I could ask you. You could easily figure it out on your own. But it's one that's, it's not, it's one we just don't kind of answer in this class. Hey, if you're looking for an extra credit project, though, there you go. Does that make sense? Does anybody have a question about that? Okay, does anybody have any comments or questions? Okay, then what I'd say is I say we end here. Work on this homework. If you have questions, let me know. I'd be happy to answer them. And again, if you need me to answer something on email, you got to send it more than once. That's just how it works. Does anybody have a question? If not, I'm going to end this recording in 5, 4, 3. Any questions? All right, then you guys have a great weekend. I will hopefully see or hear from you guys on Tuesday. Be safe and try to learn something. Question? No?